In the previous video, we talked about mechanical advantage of a simple machine. In this video, we're going to continue from where we left. This is third in the series of simple machines. We're going to talk about velocity ratio. So quick summary of what we saw in the previous video. Your mechanical advantage is given by your load by effort, and ideally your mechanical advantage would be LE by LL, but in reality since your input torque would be far greater than the output torque because of efficiency reasons, your mechanical advantage you will find that is in reality is less than LE by LL. So in this video, we're going to continue from the previous example, where we had a stone of 50 kgf and you had to put in an effort, and given was LE was 200 and LL was 20 centimeters. So let us represent that as in a simpler format. So usually you will always find it represented in this format. So this is your load, load, and this is your length of the load arm, the LL, and this is your effort, and this is your length of the effort arm, which is length of the effort arm, right? And as you put in that effort, what you will find is that this lever goes down, and as the load goes up, the effort goes down. So this distance that you find is the length of the load, the distance traveled by the load arm. This is DL, and let's assume that DL equal to 2 centimeters, and your distance traveled by effort arm, which is DE, is something that you have to find. So let's say we need to find this, find in this particular scenario what is DE. That is what we need to find. And B, we need to find what is the speed of the load divided by the speed at which the load moves up, divided by the speed of effort. Or rather, let's do it vice versa. Let's find out the speed of effort arm, the speed of effort arm by the speed of the load arm. So you can take a pause and try to find out both these answers. So if you have got the answer of DE as 20 centimeters and this ratio as 10, then you're right. So let's see how to go about doing this. So let's take in this case two triangles. Let's consider two triangles, right? You have triangle ABO, which is the first triangle, and you have A dash B dash O is your second triangle, right? So in triangle 1 and 2 are similar, and the reason why they are similar is because these two are alternate angles and they are same, and then you have both of these as 90 degrees. Now since both these triangles are similar, you have DE by DL is equal to your LE by LL, LE by LL, and that would be and we know that LE by LL is 200 divided by 20, and that is equal to 10. So in other words, your DE would be equal to DL into 10. That's equal to 2 into 10, that's 20 centimeters. So an interesting observation is that your effort arm is moving a much longer distance. Though you're putting in a smaller effort, your effort was about 5 kgf, but you moved 10 times more distance, which is about 20 centimeters. So the product of 5 into 20 would be equal to, in this particular case, your load was moved up, and load was initially 50 kgf, but you moved up by 2 centimeters. So your 50 into 2 is 100. So your input and output, they're matching up. So we look into from the work perspective in the next video, but the interesting thing is your effort arm moves a longer distance than your load arm. Now this is the first question, and the second question was speed of the effort arm. If you know distance moved by effort arm and distance moved by the load arm, it's just a matter of multiplying divided by t on both sides, and you get the velocity of the effort arm divided by the velocity of the load arm, and that won't be any different because you're divided both top and bottom by the same quantity, right? So your dE is 20 by t, whatever the time it takes. This is 2 by t, and both your time is going to get cancelled, and that's, you're going to get 10. So your speed of your speed of effort by speed of load is also equal to 10. So this speed of effort by the speed of the load arm is what we call as the velocity ratio. So the velocity ratio is equal to the speed of effort arm divided by the speed of load arm, and this is equal to your distance moved by the effort divided by the distance moved by the load, and this is in turn equal to the length of the effort divided by the length of the load. So this is your definition for velocity ratio. And unlike mechanical advantage, here we don't, assuming your rod doesn't bend at all, this is true for ideal and non-ideal, right? This is true for ideal and non-ideal scenarios. And the other interesting observation that you have is, since for ideal mechanical advantage is equal to load by mechanical advantage is load by effort, and ideally that's equal to LE by LL. We can infer that this implies that your ideal mechanical advantage is equal to the velocity ratio, right? So this is also a very, very important thing to keep in mind, which is your ideal mechanical advantage is equal to your velocity ratio, and in this case both were equal to 10. So in case your velocity ratio is greater than 1, implies that your load, your output which is your load, implies your output or load moves slower than effort. In the next video we will discuss a little bit more detail of what happens when your mechanical advantage and velocity ratio are less than 1.